Hi, Jason. Hi, Jose. How are you? Good. I'm glad to hear you're doing well. Hey, Ryan. How are you? Daniel.
Hello, doing
Hi,
fine.
Ian. Hi, everyone. I hope you're doing well. This is our last lecture. Check out the assignments and your notes. I hope everyone's doing good. We're going to
So
cover.
this is our last lecture, and from now on, it'll just be the project.
Next week, I'm going to cover final review. So I'll go through the final review on Tuesday, and then Thursday I'll give you time to do your project. So every Tuesday we're going to do final review. So check out notes and assignments, please. We'll start in a few minutes or 1 minute. Okay. So we'll go ahead and get started at 6 o'clock. Hi, everyone. Welcome to the last session for CIS11. In this week, we are going to cover Unit 12, which is going to be the last 2 chapters. Okay, so as you look at your Canvas, we are now finishing the last 2 chapters. And next Tuesday, I'm going to cover the final review. I'll post that. And then I will also post the recording in case you missed something. I will cover it in 2 parts. So I will cover the first half of the semester in the next Tuesday, and then the following Tuesday, I will cover the second part. There is a third one, but I will add that to the second part. Okay. So for Thursday, you are going to spend time working on your project. And so I want you to reserve the time to do that with your team. I will be available on Zoom in case you have questions, so you can pop in and ask questions as needed. Okay, so as you look at the notes, this is chapter 17 and 19. and we are going to talk about recursive function. While we didn't really address this in assembly, you can definitely implement it. You just have to have the function call itself. So as we go through the chapters, we are going to answer the assignment questions. Okay. So in the first part, it talks about recursion. And as we touched on function last time, we talked about function as a way that we can package a section of our code to accomplish a certain task. So you can use the function call to be able to achieve a certain task repeatedly. But in this one, what we are going to address is the function that's going to be calling itself. And so you would see this in implementation of Fibonacci or factorial or running sum. So similar to recurrence function in mathematics, we can take a look at how we would be able to implement running sum example. So in this one, last time we talked about how we would be able to implement the conditions, and we want to be able to have the value added every time, also using loops. So here it shows you how you can create a function to be able to have a running sum. So in C or C++, or even Java, you have to have a type. So here in represented in C, you would have int. This is going to be a function for integers, and we're going to call it running sum. And since we are using n, we want to put that into the argument, and then we implement the if else statement. So if n is equal to 1, return 1, else return n. And as we define the function here, when we return, we're going to have it call itself. So again, we're going to use the function name here, and we would say n minus 1. So as it builds, it's going to take the previous value and it's going to add to it. And so that way it's going to return the total for you. So here in execution, we would see that the result, right, for the running sum, if we pass the 4, it's going to return 10, as it's going to take 4, and then it's going to put the 3, which is n minus 1, into the parameter here. So n minus 1 is going to be 3. And as we call running sum, it's going to use 3 in the parameter and be able to call the function again. And so again, so when we do it here, we're going to return 3 plus running sum of 2, because that's going to be n minus 1. And then in the next one, return 2, running sum of 1. And then eventually we would have a return value of 1. So as you would see it in iteration, what you would see is we would start with 4, and then we would have 4 plus running sum of 3, which is n minus 1. And then in the next round, it's going to be 1 less each time, and eventually we have return of 1. So in C structure, I tried to pull up my repo here. Sorry, it's going a little slow because. So here is another example that you can look at, and this is in C++. So I use this in my CIS11. So at the top, we would prototype the function. So we would have int factorial, and this is my function name. And I'm using the type. So when you prototype, you just simply implement the type in the argument. And then in the main, I want to declare int n. And then I want to have an input store into n. And then I have a couple cout to display to prompt the user. So the function definition is on the bottom, as I would define what int factorial would be. And similar to what you've seen in the example, since we're using int n, we are going to have to include that in our argument. And then we would have an if else statement. So if n is greater than 1, it's going to return n times n factorial. And in that parameter, it's going to be n minus 1. So often that you would see in recursive function, we would use the previous value, and the way that we would implement that in a C++ program, we would have it as n is our current term and n minus 1 is the previous term. So here we would take the current term, multiply it by the factorial of all the previous term. And so it's going to build upon itself. Now, the downside of using recursion with factorial like this is down the line, if you don't implement dynamic space allocation, it's going to run into problems. So if I run this in C++, right, um, let's say that if I do a factorial of 6, it's going to be able to produce, it's going to tell me that it's 720. But if I use a larger number, let's say if I use 300, notice that as we have to think about how we type it in C++, because then we would run into issues with how it's going to display pulling from integers. And also down the line, you're going to see that when you're using a larger number, it's not going to be able to produce it. As that would be the issues with recursion, is that it has to build up on all the previous numbers. So therefore it's going to be slower. And if you don't have space allocation accordingly, that's going to be the flaw with recursion. And so, but it's very easy. It's very transparent as you look at the function. So in this one, we just simply take the current term, multiply it by all the factorial of all the prior terms, including the previous term. So here's the previous term, and it builds on its previous term, and so on. So as it does that, we have to have a function that calls on itself. Okay. So this shows you an example of it that would be in C. And then in your notes, it shows you are running some example in illustrations. So another example that you would see using recursion is in something like a binary search, where it would be able to take the set of data, set of values, and then it's gonna break it down into half and half again until it gets to the single element. And so as it does that, right, what we want is we want to implement a function that's going to be able to search for the value using recursion. And there are many different ways to approach binary search, but this would be another example. So here, as we break it into half, we would then look at where the half point would be as we divide it by 2. So if you're looking at an array, we have to look at the beginning element to the end of the element, and then we would chunk it into half. And so we would then have to implement the conditions. If n is less than the start, okay, then the exam would be not on the stack. So it's going to be that it's not going to be found. Else if, so in this case, we're looking for student name, right? Student name is going to be in the name of the exam half point. So if it's in half, it's going to actually find it in the first half, okay? Else if it's in the lower half on the second half, then it's going to search there. Okay, so this is a way that we can divide it into subsection where we would be able to find a student name by cutting the list into half and then half again until it gets to the smaller number of elements so it can search. So now why is it using recursion? So because we're doing the half point minus 1, right? For the else if here. So for the find exam, it's going to pass the student name, start, and the half point minus 1. Else if, it's going to search the upper half where it's going to be the half point plus 1. So that's how it's going to be able to distinguish which half it's going to look in to find the student name. And binary search is the one of the most efficient search algorithm that can be implemented when you're seeking a value. Um, and so when we're looking at this, if you write it out, if you're able to set it up and within pseudocode, you will be able to implement it, and you can implement recursive function. Okay. And the third example that I want to present to you is Fibonacci. And we've done Fibonacci already in assembly, so you kind of have an idea. And in this one, we're seeding at 1 and 1, right? And in Fibonacci, we are using the two previous values and we add them together to get a sum for the next value. So here you would see the representation of the previous value with the n minus 1, and then the value before the previous value, which is n minus 2. So in order to find f of n, we have to add those two together to get to the next one. And we would have a starting point where the first two is going to be 1 and 1. So we seed at 1 and 1 instead of 0 and 1. So when we add 1 and 1 together, we should get the third value, which is 2, and then 1 plus 2 to get to the next value, as we covered in the lab for Fibonacci. So here you would see how Fibonacci would be written out. So here you have a function called Fibonacci. And again, using int n in the parameter. Then we can say if n is equal to 0 or n is equal to 1, it's going to return 1. So if it's the first term and the second term in that sequence, it's going to give you 1 because those values are 1, right? We're seeding them at 1. We start at 1 and 1. That's why that condition is there. Okay. And else, then we're going to return, right here is where you see the function calling itself Fibonacci of the previous term plus the term before the previous term. So you're going to get the sum. So as it builds out the sequence, it's going to take the two prior terms and it's going to add them together to get to the next term. So here it lays out the actual step. Now, in assembly, as you remember, right, as you are working with sequence or a container that would utilize different values or different numbers in the elements like of the array, you have to be able to save and restore the values, right? And all that is we are associating that value with a certain location in memory, and we would then go retrieve it every time that we need to use it. So in the main call here, you would see that when we're using fib3, right, it's going to use the R6 to determine what's on the stack. Okay. And then when we're doing fib2 and fib3, as this gets pushed in, it's going to then update the R6, the register 6, with what's on top of the stack. Okay. And so on. So as you would have multiple calls, what we can do is we can have it push into the stack, right? And then when it operates that, we would use one of the register to really determine which one is at the top. We talked about this in the last couple of weeks. And then we would be able to actually calculate and use the stack as a way to abstractly, it's an abstract level of storage where we would be able to refer to the section of the memory where it would store the values. Okay, so here it shows you that when it's invoked, it updates the activation record as it pushes it onto the stack. And we would use our register 6 as a way to meter, right, which value would then be pushed onto the stack as it would call on, as it would have a function call there. Okay, so when you're calling then it's going to update the activation record as it's pushed onto the stack. So after it return, right, it's going to also update that, and as soon as it does that, it's going to pop it. And we touched on that last time. Okay, so here it gives you a visual illustration of how that would be when you have the calls, and then when you have the next call and the next call, and so on. So coming back to the question, for number one, it asks you what is recursion. And we can say that it is a method of solving problem where the solution depends on solutions to smaller instances of the same problem, requiring the function to solve the task by calling itself on smaller pieces of data. So it would rely on the prior result in order to build the next result value. And so when we build these type of programs, we have to think about where is it going to retrieve the values from, all the prior values, right? And even when you're looking at like binary tree program, binary tree search program, or factorial program, in some of those programs, if you see that the programmer implement data structure, you would see that they would use pointers, and they would, you can implement things like doubly linked lists, things like that to really allocate specific area where you would be able to store the values and be able to retrieve the value. Otherwise, you would see that there's inefficiency in how you use recursion. Okay, so it would be best implemented with data structure. And the example we looked at, so for number two, it asks you to provide an example of a program that uses recursive function or subroutine. And you're not limited to this, right? There are other examples, but the common example that you would see is going to be sequence-based computation, which is like Fibonacci, Lucas, factorial, running sum, or in random number generator. Any question with number one and number two? So for number three, it asks you to describe how recursion can be incorporated in programming, what happens on the stack, and what is contained inside the activation record. So we can say that when recursive function is invoked, new activation record is pushed onto the stack. So it's going to update the activation record, right? Once the value is returned from the first call, it is used in the next function call, updates the activation record for the push before the next call. After the next call takes place, the activation record is updated, then pop from the stack. I should say from the stack. Okay. So first, when the function is invoked, we say that the activation record is pushed onto the stack as it needs to update. It needs to pull the the um, the parameter variable, like the argument, right? The argument those are the variable that's being used, if you recall from last week. So those get added to the activation record. Therefore, it needs to push the activation record onto the stack. Then once you have the value returned from the first call, then the function is being used, right? Again, so it is used, the activation record is then being used for the next function call. And in assembly at that point, the R7, it's gonna the register 7, it's going to be used with the return and also bring your program back to where it should be for the next function call. Okay, so we talked about how the value, the return value using register 7, and then how that, it updates the address of where that function call, the next round for the function call is going to take place. So at that point, it then going to update the activation record for the next round, which is then it's going to push in the activation record before the next call. As it is the same function, it already has those, the argument variable in place. So it's then going to push it back onto the stack, and then it's going to execute after that next call takes place, right? So as it goes through, and then when it completes, the activation record is then updated that it completed the execution, then it's going to pop off the stack. So in summary, I put a few sentences there for you to see the process as we covered this last week as well. Okay, any question with question 3? All right, so let's come back to the notes here. Here it gives you the details and also illustration with Fibonacci. Okay. And as you can see, when we return, right, the next one is going to be call. So when you look at this, what will happen is it's pushing these on, and then as it finish, right, it's going to pop off. So as you can see here, it already popped up the top one, and then R6 is updated for the next function call. And then once that completes, then it pops off, and then R6 is going to go to update for Fib3, and then it's going to pop off. So because it's going to be first in, last out. And then when you're done, you're left with just the main. Now in C++, we don't really have to worry about this, right? We see the compiler handle this. But in assembly, we have to really set up a stack, and we would be able to write the process and how it would push it onto the stack and pop it off of the stack using label and subroutine. So here, as what we saw last time, you would see the temporary, this is going to be the temporary variable. It's a location where it's going to hold the result. That's going to be its local variable to that function. And your argument is here. Okay. And then we talked about dynamic link return address and return value. This is part of the activation record. So here we've done Fibonacci, but this is another snippet that you can see. And so now this is, keep in mind, again, this is just a snippet where it just shows you on how it was, they set up for the push. Okay. So here, what they have is they have add R6 with a negative decimal 2. So they put a comment, skip return value, push the return address, because when you look at the previous, okay, if the top is here, your return address is going to be 2 offset later. Okay. And then following that will be your return value and then your argument. So recall that last time they referred to this as X. It's going to be where that gauge is at the top. So when you look at this code over here, right, your R6, it's going to move down 2. So it's going to push 2 and 2 lower. That's going to be your return address. Okay, store whatever that's with the R6 to R7, because R7 job, your register 7 job is to do what? It's part of the return process, right? It's going to update where the program would pick up and how the values would be returned. Then it's going to go to -1 because if you look at this give you a good visualization. So if we're here, we're going to be -2, we're actually here. And then we're going to come back up to the -1. That's going to give you the dynamic link right here. Okay, so that's what they're referring to when it's pushing -1. It's -1 as the offset. And then again, we are going to store that, but in this time, it's going to be to register 5 because register 5 is going to help you set up your pointer. Okay. Then from register 5, we're going to do a -1. That's going to be your pointer. So come back. Okay. So then we are going to come back to here where it's going to be we're going to point to where our value is going to be. And so it's really when I explain assembly, if you can visualize it physically, right? Because all of this is at an abstract level, but if you think about like how it's going to sequentially move up and down that set of memory addresses, that's how you're going to be able to use, right, values like this to be able to get it going from one part of the memory to the next part of the memory. And that's what we're trying to illustrate here. So when you go through, as you can see, when it adds this, and now this doesn't have to be the only approach in how you do the push, right? If you compare this to what I've written for push or other people have written for push, it's a little bit different. It depends on how you start your program and how you move through your program to get to this point. But this is also another way. So what I'm presenting to you is, yes, you can write your function this way, your recursive function for Fibonacci this way. Okay. So then for this, where we would be space for the local and the temp, so you've got to move down to the int n, that will be -2. So as you got to n, you got to load it. So you have to load the n to register 0, so that way you can check for as you branch. Okay. Is it the last round? That's what it's checking for. Okay. So when we look at the case, when we say if n is equal to 0, return 1, right? If n is equal to 1, return 1. So you have to implement the branches for those conditions. Okay. So sorry about the whiplash now. Okay. So coming back to Fibonacci here, see these two? You have to branch for these, because if it's 0, right, you check for 0. If it's 1, you got to subtract 1 and check for 0, or you can check for positive. It depends on how you want to branch. So here in the function, we got to tie this condition in, and then we can, otherwise we are gonna have it recursively the recursion call right here. Okay, so that's why you see the branch here. Okay, so as it load n, we want to check what for, right, um, the if, and then we subtract the 1 and see if it's 0, then that's going to be equal to 1. And so when we, in the next one, it's going to read the parameter. So when you load the 4, this is a register load. So you load a 4 with whatever that's in R5. And what was in R5? R5 contain N. So this is the way that we would use the int N in the parameter. Okay. And we would load that into register 0 because we are going to use the register 0 for the next one. So now we want to take that N and we want to represent N minus 1. So N is now in register 0. So then here we would say minus 1 to indicate that it's N minus 1. Okay. And since R6 has its, remember that's, I call it the meter, but it would be like where you should be in the memory address. So when you're pushing that R6, its job now in this particular program is going to be how you're going to use the stack, right? That's going to, its job is for stack use. So when you, at that point, you have R6 as N, so then you have to have it subtract 1 to get it push N minus 1. So that's why you see that it's add -1 here. And then we would store it to register 0, and then we call it self. So at the end of that subroutine, you do a JSR Fibonacci. And what that does is it's going to come back at the beginning and it's going to start all over again. Okay? It's going to keep doing it, and it can infinitely go forever. Question. So after we call the subroutine, right, we got to clean it up. So the next part is going to be the pop. Okay. So as it does that, when you look at the previous diagram, they show you that it pushed the activation record, right? And then as it executes it, it's going to pop it off. So it's going to do that every time. So here we're going to load the return value. And that was coming from the stack. So it's going to be R6. We're going to load that to a register 0. We're going to increment that. So it would be a location where it's going to store that. It's going to be a +1, store in temp. So from R1, subtract -1, and then, or add -1 and store that onto register 0. So we load here, we store here, but we load from register 6, we store from register 5. Then we are going to read. Okay, so when you read, you are going to load again. But in this case, we're going to read the parameter for N. So whatever that's in N, it's going to read the value. Okay. And then this represent N minus 2. So as earlier, remember how you push N minus 1? So you need to push N minus 2. And the way that we would do N minus 2. So here is N minus 1, R0, R0, -1, R0, R0, -2 for the N minus 2. Okay, so pretty much the same. The only difference is the -2 to indicate 2 terms prior. This is 1 term prior. And then since you have N minus 2 now, you are going to push it. So, and then you're going to store it. Okay. Then call itself again. Okay, so this section is for n minus 1. This section is for n minus 2. And then you got to pop it on the top. I believe that for assembly, this is the hardest area to really understand because especially when you have a lot of movement across load, store, and then call, load, store, and then call, especially when it's recursion. And in Fibonacci, you don't only have one prior value, you're using two prior terms and sum it together. Okay, so this is why you see people, instead of using recursion, they would do like iteration, set up an array and then iterate through it. Okay. All right. Let's move over to the next part. So here, this is the last part is for the pop. Okay. So when you finish, you want to check for, here they branch it with -0 and positive. And the way that this code is written, that it's going to be going to the end, and fib end, it's going to pop it. So you can do it this way. I think, in my opinion, I wouldn't approach it this way, right? I would have a push and a pop, and then I would use a function for the push and the pop, and I would nest that function inside another function. So, or a subroutine within a subroutine. So I would do it a little bit differently. But so what they did was they use a label called fib_n, and if it branched, they sense it here. And then in this section, it's going to pop. Okay, so when it's finished, it's going to get rid of it. And before the process, this is going to be for the return one right here, for the base. And I would take this and put it earlier in the game because the if condition happens actually earlier in the game. Okay, so it's really depending on how you look at it and how you want to approach it. Every programmer look at it a little bit different, right? And so this is a good example that you can look at on how you would use push pop for stack with recursion. Okay, any questions with the things we just covered? Okay, no question. So in the next part, we're going to talk about data structure. And for C++ or C, you see struct, right? And it's a way that we can group things together in a structure. So data structure is a way that we can organize data in memory. We can group related things together for the purpose of computation in our program. We can organize data in bundles. It's just a convenient way and efficient way to execute our program. And array is a container that would be able to store values, but that is usually at elementary level, right? We would move into different ways that we can organize our data in the program. So in C, you often see there would be struct, and it's a way that we can group related items together. So in the example here, you have different type working together. So let's say that I wanted to create a program to calculate the dimension for an aircraft, right? I have char for flight number. I have int for altitude, int for longitude, int for latitude, int for heading, and double airspeed. Well, we can use struct to group them all together, and we can make it into, when use that structure to create a new type. So, oops, sorry. So here we can define a struct. So struct flight type. And then under that, we would indent in, and then we would group all of those things together, and we would enclose it with the curly brace, right? And you usually cover this in CIS5 or 17A, like Introduction to C++. And we would need all of these variables to be able to, we are using all of these variables in our program. And now we can create a structure called flight type, right? And that will be grouping them together here. Okay. So when we look at how that will be set up physically, okay. So here you would have your variable, right? Your char for flight number, altitude, longitude, and so on. But at this point, what it's going to do is, because remember, if we make it into a structure, it's going to take on that new type. Okay. So we can say that it would be plain.flight number, plain, right, dot altitude, longitude, latitude, heading, and airspeed. So what that does is it says that it's going to really, when you create a struct or a structure in the program, it's going to tell the compiler how big of the structure would be and what kind of different type of data or members that you would have in that structure. Okay. It does not allocate any memory, but it allocate for the struct in which you would have declare member variables for that new data type. So when you declare that struct, it creates that new data type and it allocates the space for that new data type. And in that space, you would have the member variables, right, that you group inside, right, that structure. That's going to be allocated and used based on that structure. Okay. So at that point, we would then be able to access individual members in that structure. Okay. So it would be something like this. Okay. So you need to type it and then you can give it a name. Okay. So let's answer the next question. For number 4, data structure in C is an organization of data and memory that group related items together. I have forgotten the word to achieve programming convenience and efficiency. And a struct is a mechanism for grouping related data items of different types in C and C++ programming. So here I have an example and you can create your own example, right? Let's say that I have a program that computes, total price for a certain amount of food that the customer purchased. So I have a struct food, and within that I would declare, I forgot my curly brace closure there. I would declare my member variables. So I have double weight, double price, string description, and int size. And you can have your own program or example of a program if you want, but that would be a simple example. So another example would be that, let's say I want to create a program that calculate dimension for a container, like a cylinder, right? And I might have like inch height, right? Inch radius, um, or even double radius, and so on. Okay, so I can say struct cylinder, right? Inch height, double radius, right? And etc. So you can add in the variables there. Any question? Okay, so for 7, we want to describe how memory is allocated for a struct. It allocates storage for data dynamically as needed. And it uses pointer to implement contiguous memory allocation of members in the struct. So that means that there's no actual fixed size, right, to start with. So it's going to determine, the compiler, it's going to determine based on how much is needed depending on what type of members you have in that group. So it would use the pointer to be able to set up contiguous allocation, meaning subsequent memory location for the members in that struct together. Okay. Any question with 7? So here, if we take a look at the program, right, we say int x flight plane, int y flight altitude equals 0. So here's your y, okay. Plane flight number is here, and then you got the subsequent member variable here, and then you got your x here. So in the LC3, right, we clear, and then we would want to be able to have R0, R5, negative 13. That would give you the setup for plane, which is going to be the type here. So you have flight plane. And then since it might be a string, right? So you would need to have each of the char value as the location, just like what we did with Monday, Tuesday, Wednesday, Thursday, Friday, day of the week. You guys remember that, right? So what you need to do is you need to set up an array where it would have for the plane, where it would be allocated 1 per, okay? So here we would have negative 13. And then it's going to store. Now, for the assignment of this, they cut off a lot of the things so you don't see all the things that would be prior. So here's just a small snippet. Keep in mind that Like there are things that we don't know about, like how is this going to be for a specific thing, like just flight number? um, how is are we not loading the string? So there are things that we don't know coming in and leaving this snippet. Okay, so this is a very small snippet. I didn't agree with the person who create this because it doesn't really give you the detail in the actual program. But when you store it like this is just going to give you like some piece in the flight number. Okay, where it would be from here to here, from 0 to 6, that will give you 7. Okay, so one character per, and so that way you would have eighth of the word. So that's why they're using 7 here. So if you start here and you finish here, that's 7. That's each character is going to be for your flight number. Okay. Any question? All right. So here it talks about the array. There's 7 words in this case, and that's what you see with the representation with the adding 7. Okay. In order to access the particular element, the way that we would look at it from an array standpoint is we would index it, right? Here is where you would use the index. So then when you have the dot operator that in the same precedence from left to right, that's just going to indicate that the value at that index, right, is going to be utilizing this property that's assigned this value. Okay. And so when you access the member, you simply use the dot notation. Okay. And I can have latitude, altitude, longitude, as those are going to be members of that type. You see this being used more apparently in Java compared to C or C++, because the way that C and C++ is really used is we would see that in like struct or, in some case if we're accessing classes. So it's really tied to like the object and the class and the structure of the data. But in Java, when we implement the method, we can actually, right off the bat, you have to use class. And so you would see more often that we would use the dot operator to access, the members or the property of the object that way. Okay. So another way that we can do this is we can use pointer, right? Last week we talked a little bit about pointer. So the way that we can declare a pointer for a struct is we can say flight, and then you would know that it's a pointer using the asterisk. Okay, and then we would say plane pointer, and then we can say what plane pointer would be, and here we would use reference. So ampersand, and then planes, and then whatever the index. So in this case, we're using 34. Okay. Now, similar to the last one that you see here, when we're using the pointer, we would simply put the pointer in as the parameter here, and then we would access its member altitude. Okay. Now, this is different than this. because it tells you here that the operator has higher precedence than the asterisk. So therefore, when you're looking at this, it's different than using this. Okay, so here you're passing it, and then here you're using the pointer and accessing the member. So in the next question, it asks you, in an array of structs, how is the member accessed? And we can use pointer, so you can use through pointer, as we looked at that. So coming back to here, in the section of the notes that you can look at is this right here. Pointers in struct, and in the array of struct. Actually, I'm going to change my answer real quick. I don't think it's... It should be using the dot operator. Okay. And to access individual member, we would use the dot operator. Even if you're using the pointer, you still have to use the dot operator. And then for 9, describe how the struct is passed as an argument in C programming. It is passed by the value into the function. Then the members are added to the activation record of the function, but not copied. So when it's passed, it's going to give you the value of the function. So when you look at where the activation record is, it's going to reference the argument, which is what is being passed. Okay. So now, because a struct then is a new type, so when it's passed by the value into the function, all of the variables inside that struct is going to get added to the record in as an array. Okay. So it's going to add all of those into the record, but then it's not going to be copied because it's going to be able to use what they are in the record in order to give you the result. So therefore, when we're using the dot operator, what it is it's going to use the activation record, and it's going to find that on the stack to be able to use it. So it's going to push that onto the stack, but not copy. Any question with this? So in any type of program, as you can see, it's going to come down to, at the end, is going to be the data structure piece. So you can write the program, but if you write the program with data structure, then you would be able to maximize the capability of your program. All right, so here, it shows you passing the struct as an argument. It says, unlike the array, the struct is always passed by the value into the function. Its members are copied. So that means that the members are copied to the activation record. Changes inside the functions are not reflected in the calling routines copy. So it's only going to take effect in the activation record. Okay. And you want to pass the pointer to a struct. So we talked a little bit about dynamic allocation. This gives us the flexibility in how the size would be adjusted based on, you know, whatever that we need for our program. So allocate storage for data that's dynamically, it's going to be as needed. And that is probably a better approach than just section a certain memory and waste it. Okay. So you probably seen this before. I know that when I teach 17A, I address this. So you've seen this in C, where you can use that to allocate memory for the runtime using Malloc. Okay. So what that does is it's going to give you contiguous region of memory. That means it's all going to be together consecutively for a request size in bytes. Okay. So if this is int, it's going to give you the size for the int. And the bytes are located in the region memory called heap. Okay. And it keeps track of the memory from the heap that's been given. So when you look at the stack and the heap, okay, this diagram is important because I think a lot of people still don't understand this thoroughly. So if you're looking at the C compiler, it's going to manage this. Okay. Now, this is not executable, but it's writable. We can store things here. Okay. So is the dynamic data section, which is the heap. But this is being managed by the programmer. Okay. And then when you declare your variables and all of that, your literals, and you assign, you initialize value, like I say int n is equal to 0, that's happening here. Okay. And then your instructions, so when you have instructions, you know, if you look at assembly like add and so on, that's down here. Okay. So how does it execute? It's basically, it's going to refer to that section of the memory. It's going to be able to pull it there. Okay. So this is executable because it's instruction. This is not executable. It's only going to be able to read the value, right? This is just going to store the data, and store the data. And stack is used for activation record, right? So here, what it says, it tells you with the heap right here is that we can set up a section of the memory that's going to be allocated for something. And that is going to be user control or programmer control. Okay, this section. And the stack, it's going to grow and shrink, right? Like we can push and pop it. So as it's going to grow, and there's also going to be a limit. And then the heap, it's going to grow and grow, and there's also going to be a limit. And we want to control that. Okay. So this is just a visual way to really illustrate this so that way you can see it in 2D. So when you allocate the bytes, okay, it's going to be able to, it's going to calculate the size based on your data type. Okay, so that will be based on the type of data that you give it. And in the case where if you need to change the type, then you can do things like casting, You're probably familiar with like typecasting. Okay. But you can cast it into a different type. You can go from int to double and so on. So some of the things that they wanted to point out here is that once the data is no longer needed, it should be released back into the heap for later use. With the stack, it actually pop up, but with the heap, what we can do is we can have it put back into the heap for use. Okay. So for 10, yeah.
The malloc and free functions are the C equivalent of the new and delete keywords in C++.
New and delete is really for you to do what? You can construct an object, right? But malloc and is not really just to construct for the object, as you can see. Okay, what that does here in C is that you can just section a size of memory for a certain purpose. It doesn't necessarily be for an object, right? Because C is not object oriented. So it doesn't, yeah. So when you construct for an object, the purpose of the object is to do what? To use it to access properties and classes, right? So when you deconstruct the object, you release back that memory space. Yes, that will be something that you have to do to clean it up in C++. However, it doesn't necessarily, you can't construct an object in C. So if you compare that in equivalent, not quite 100%, because C you don't have an object in C. It's not an object-oriented language. It's just a way that we can section a memory for purpose of heap, which is how we would use it. I have a chat message. Right. It doesn't call, yeah, it's not a constructor. So if you're looking at the equivalence in that, there's no equivalence in that because C doesn't have, it's not an object-oriented language. C++ is, right? Java is. So it's just a way that we can set up memory allocation. Malloc is memory location for things that we want to work with. Could be different type of data and so on. Okay.
Yeah, the equivalence is just allocating and deallocating memory, but yeah, there's a difference there with C++ having objects and C not
Right.
having objects.
But in C++, you do have typecasting, right? Like, and you can go from one type to another, and sometimes it automatically typecasts it for you. And so you can force it to cast, right? So you do see some similarity in that, in the casting area, but in this, because they don't, it's just a way to use memory for heap. So that's how you would use malloc. And since C++ is built on C, you do see some relevance in that too. Like you can still use some of the C function in C++. You see what I mean? Because it's built into the actual library or the built-in library. But the need for that is not so much the way that we use in C++, because we can have it structured differently. The way we organize our data can be different. We can focus more on the object and how we would use that object. Okay. So the book uses C is because it's a little older, and C is commonly taught throughout all institutions. So Something that you will still see in C++ is your linked list or doubly linked list. Okay. So what you can have is you can have a linked list, which is an ordered collection of nodes that would contain data, right? The difference between a singly linked list or a linked list compared to a doubly linked list is that on the single linked list, which is n, it's going to go from node 0 to 1, 2, 3, 4, 5, and so on. It's linear. Where doubly linked list, it comes back, it circle back. So at the end, let's say node 2 is the end, it's going to tie back to node 0. So you just simply point it back to node 0. Okay. And we can use each node, right, to contain some piece of data. And you can link them together. That's why they're called linked lists. Think of it like a train, right? You have each car that holds different product, and you would link them together. Well, on a singly linked list, you would see from node 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10 would be the last one. So on this last one, you would have a null because you need to terminate it out. You need to say that this is the last node. On the doubly linked list, it's gonna come back, it's gonna circle back from the last node to the beginning. Okay, so it's gonna point back to the node 0. Okay, so that's the difference. And the first node here, node 0, is gonna be the head, and the last node is gonna be the tail. On the doubly linked list, there is no tail. Okay, so it's gonna come back to the beginning, and that's what you have with the doubly linked list. So as I said, it's sequential and it's accessed sequentially. So think of it like an amplified version of an array. But you have the container, it's a container that has container within, and they are sequential. A glorified array. Lack of a better word, I should say. Okay. But the cool thing about the linked list is that it's dynamically allocated. So it sizes it to what you need, and that's what you want. You can add the node as needed. So you can sequentially add it to keep it organized, or you can also add in the node. And this is what you see in the large scale on how they would implement container that would store large amount of data in an application, right? You would implement data structure like this or better, okay? And then you can also remove node too, okay? Add or remove. And so when you're looking at, because this is often taught with like binary trees and all of the concepts with data structure in that, because when you're looking at a self-balancing binary tree, what happens is it's going to make sure that it's going to equate on both sides. Like it's an abstract level of how you would balance your nodes from one side to another compared to other type of binary tree, right? Because the binary tree is going to grow outward, but in the self-balancing binary tree, all the nodes from the left side and the nodes on the right side are always going to be equal. So if you are removing one on the left, it's going to also have to remove one on the right. So in that, you know, you would implement the conditions on how you would be able to point to which one is how it's going to traverse back into the node. Okay, sorry, I just want to give you like a data structure example on how that would be. But, you know, on that, you can apply it, and you can definitely write binary tree using, you know, container like these. Okay, so here it shows you how you would be able to add in the node, right? So you would need to disconnect the link, terminate the link here, and then you would point to the new node, and the new node we're gonna then point to the original subsequent node. So that's how you're gonna be able to add it in. splice it, they call it. And then whichever one's going to be the last is going to be null. So it's going to terminate. And you see this concept being carried in communication systems in a lot of things. So when I teach stuff like networking and appliances, communication appliances, you see the computational concept carried into that on how it's linked together, the type of data that's being passed from one system to another. It's very much related to this in how we represent data structure in programming. Okay, so for the next question, it asks you to define the linked list in C programming. And it is an ordered collection of nodes in which each can contain some data, and it's connected using pointer. And so we just abstractly use pointer to associate, right, the link with memory location as we would represent a linked list. And compare and contrast linked list to array in data structure. Linked list size is dynamic. Data is accessed sequentially. It is easy to add and remove nodes. Array elements is easily accessed. Outside of dynamic array, like your array in general, it's going to be fixed size. Okay. Or I should say size is dependent on number of elements, right? That will be the size of the array is the number of elements that would be. And then each element can be accessed using index. All elements can be accessed using iteration. So you can loop through it, right? Now, and that would also be a sequential approach, right? You can go from 0 to X number of elements. And in that sense, linked list is similar in that it is sequentially accessing the node. So you need to go from node 0 to node 1 to node 2 to node 3 and so on. And then if you need to add the new node, you need to disassociate the link where you change the pointer, point it to the new node, and from the new node, you point it to the previous node that was linked. Okay. Any question? So CIS11C is the class for data structure. I know some of you have taken it or you're currently in it now, right? It is one of the harder class to take as it requires you to really think at abstract level. But like I said, assembly has a lot of the layout in how you would be associating memory location. It's all about memory, right? How it uses memory ultimately. So doesn't matter what type of language you see, but you see in assembly, it's the background behind the scene where the compiler does the job. Okay. All right. Any questions relating to this? Okay. So here it just shows you additional things, content about new node and linked list. And then, so for the data structures, as I mentioned, you see that implemented in trees. And for computer science, by the time you finish your degree, you should already know how to write binary trees, different type of trees, and then also hash tables. You know, that would be implementing data structure. There are tons of stuff. And even when you're looking at like graphs and traverse graphs, like when I teach CIS11, I really go into the very basic in graphs, like to really look at it mathematically only. Um, but in data science, or even, you know, when you look at machine learning or, you know, AI, stuff like that, a lot of the times it's going to come back to the basic understanding, which is going to be data structure, where data is stored, how data is retrieved, how it's accessed, and so on. Okay, questions? All right, no question, huh? So one thing I want to remind you, there is a homework assignment, unfortunately. I know. This is going to prepare you for quiz review. So take a look at the questions, make sure that you complete them. There's no lab this week. Work on your project. Okay. And then I'm going to post the final review next week so we can work on those. There is a quiz coming next week. Okay. And that will be our last quiz with the quiz game. And that is all she wrote for today. Any question? Okay. So if you have questions, you can pop in on Thursday. I'm available during our lab time, or you can see me during office hours, etc. Type in your name in the chat. Thank you, Kenneth, for start. I will see you maybe on Thursday or next week. Take care.